Hello.
So we can start, right?
Yeah.
Test, can people at the back hear us?
Hello.
Okay.
Yeah.
So I think we can start right now. Hi, everyone. Thank you for attending our session. I'm Nick Huang, here is my colleague, Saurabh Dixit. We're both from the data engineering team of Yahoo Mail. What we are going to share today is the data systems, in particular, a huge Hadoop warehouse that we have built for the last 2 or 3 years that is designed to drive the growth and evolution of the Yahoo Mail. First, I will go over the Yahoo Mail business, especially from a data perspective. And then I'm going to cover 2 of the systems that we have built. One is what we call Mail on Grid 2.0, and the other is called Mail Analytics 2.0. These are fairly complex systems. In the amount of time we have, we only want to highlight certain things that we hope are of interest to you. So first of all, Yahoo Mail. As a consumer-facing product, Yahoo Mail offers a lot of storage for the users, 1 terabyte, which is orders of magnitude more than our competitors. It also has a fairly well-received universal mail client, constantly winning reviews, great reviews on various app stores. It's a global product. It supports 46 languages in 70 markets. But what's more interesting for you guys, I guess, is what does it look like from a data perspective? It's pretty huge. It's got 200 million users per month. Every single day, there are 26 billion emails or email attempts trying to get into our system. The vast majority, 80% of which are spams. This is what sometimes we call the human versus machine 1.0. We've always tried to use data to fight the spams. Also, from these 200 million users a month, they are highly engaged with our product. 20 billion engagement events per day. And engagement events are things like the click, the swipe, the read, everything they do on the apps. Also, the entire corpus of the mail is pretty big. 250 petabytes of user data in production. And it's also a very rich data set. For example, just the purchases alone that are logged. Think about your Square receipts that you get mail when you go to your grocery. A single year, just the purchase alone, we log $17 billion worth of purchase. Essentially, your mail, one could argue, has become a lot of people's personal database. So with that kind of scale and the richness of the data, we embark on the second incarnation of the data system that's driving its growth and evolution. What we call human versus machine 2.0. It turns out, of the 20% or less of the emails, of the 26 billion emails every day, 90% of them are actually also generated by machines. These are your newsletters, social media notifications, travel reservations, purchase receipts, billing statements, etc. Because on the other side of the inbox are machines, we also need to use machine learning to help the users keep organized. And these attempts materialize themselves in the features that we offer. For example, Smart Views is a feature of Yahoo Mail where it tries to classify the emails into their different natures, whether they are emails from actual people or they're emails from social, travel, shopping, finance. Another example, notifications. A lot of people, they only want to be notified when their friends are sending emails to them. But if it's just a machine like their newsletter, they can wait. They don't need to be notified. Another example is contact images. This helps users to read their email in a more pleasant way. We have icons of the machine-generated emails right in front of the users. So with that as a context for the business, I'll hand over to my colleague, Saurabh, to talk about this petabyte scale warehouse that we have built to facilitate machine learning. Saurabh?
Thanks, Nick.
Is your microphone working?
Hello. Yeah, thank you. So I'm going to talk about system design choices and overview, and probably also going to talk about some war stories and takeaways. But before I do that, let me walk you through the system needs as what was existing already before we started this project and what was required to be done. So what you see on the left there is various data centers. So as you would expect, Yahoo Mail has a very large global footprint. So we operate from several data centers or locations worldwide. And what we had actually was one of the Yahoo Mail subsystems had an eventing mechanism in all of the data centers available locally. So we could have consumed these events locally in all of the data centers, but some of our requirements needed a global view of data, which meant that we needed to build a global data store, which is what is shown in the right. And on this global data store, then we intended to run a lot of reindexing, a lot of indexing logic, a lot of analytical workloads, a lot of machine learning and data mining workloads. We also had some use cases where we needed to run some near real-time streaming processing. This could be some indexing workloads or even some kind of alerting workloads. So what's clearly missing from this diagram is, okay, there's all that data is available in all those data centers across geographies, and we want to do all this processing in the batch processing and stream processing systems over here. But how are we going to get data from these data centers over to one single data center for batch and stream processing? And the second question is, how are we going to package that data while we send this data across data centers? And the third question was, like, how are we going to store that data when the data finally lands onto the destination data stores? So to that effect, next I talk about the design choices we made for transport, serialization, and compression. So for transport, we use DHR, which stands for Data Highway Rainbow, which is Data Highway Rainbow is a petabyte scale event collection, transport, and delivery mechanism at Yahoo. It transports data from data centers to data centers. It's a very reliable service. It can deliver data to both batch destinations as well as streaming destinations. For batch destinations, Data Highway deposits data onto HDFS via HDFS proxies. And for streaming destinations, it has the ability to deposit data onto Kafka or directly onto Storm using HTTP spouts. So Data Highway Rainbow is a battle-tested system here at Yahoo. They transport about 800 terabytes of uncompressed input data daily for various systems, various revenue and non-revenue systems at Yahoo, and about 250 billion events per day. The reason I mention more about Data Highway this time is they had talk at Hadoop Summit yesterday, where Neelam Sharma and Hubing Yin presented Data Highway in more details. If you guys are more interested in Data Highway, probably after the conference, you should definitely check out for some material online. The next design choice that we made was using Avro while transferring data over Data Highway. Some of the reasons, some of the things why we liked Avro very much was one, Avro supported this strong notion of a schema, and that meant that we could throw off a lot of bad data or protect against some of the bad data right up front. Avro provided for a very graceful schema evolution. That basically meant as a data provider, we could evolve our schema independent of the consumers. As long as we maintain the compatibility of the schema, our consumers can continue to use their old schemas while consuming the data. And that not having that step locking with consumer really made changing schema a very easy process. Our transport mechanism, which was DHR, which we talked about earlier, that also supported Avro schemas natively, and it also provided for schema registries, which it had to use for its internal purpose. One of the good things about Avro is the Avro object container files have writer schema embedded in them, so there's confidence that you can always read an Avro file that was written out. And last but not the least, in favor of Avro was good support in Hadoop ecosystem. There's enough toolset available out of the box to manipulate Avro data using MapReduce or Hive or Pig. So the next design aspect, the design choice that we had to make was about storage. This was a particularly important topic for us, especially given that we were dealing with a very large amount of data. Also because this was one aspect which was very easy to select but very hard to change later on, because once the retention was built out, it's not so easy, and consumers are already using a particular format. It's not so easy to just change the data format. So early in the project, we conducted a lot of experiments. We tested out a lot of different file formats, a lot of different compression strategies. But before I go any further, maybe I should throw out a disclaimer saying that, hey, these results are very specific to our own data sets and should probably be taken with a pinch of salt. So what we did here was we tested a lot of different row major file formats, Avro files, sequence files, delimited flat files, all the compression codecs that they supported. We also tested out ORC with zlib, Snappy. This result here is a summary of our findings. Most of the row major formats, sort of the results were in line. So what you see here on the table is in the first column, is the compression factors, but by natural I mean the data was compressed as is without any special sorting. And in the second column, what you see is in this case we had sorted data so that it would cause a lot of repetition in a lot of attributes in the data set. So that gave a much better compression factor. So as you can see here, bzip2 with natural order was about 9x compression, but bzip2 with sorted order was about 17.4x compression. ORC kind of was similar to gzip, 6.97x compression for natural order, but for sorted order it was about 10x compression. So from this slide, it looks like bzip2 is a clear winner over here. But when you look at the query performance for the various storage formats, what really stands out is bzip2 was at least 2 times slower for a lot of our reference queries compared to the legacy implementation that was available with us, which was basically a delimited file with gzip encoded. And in this particular table, you see that ORC with zlib, that combo performed excellent. Compared to bzip2, I think the performance was like 25x. So overall, ORC provided a nice balance between space and speed. So we decided to stick with ORC and zlib for our long-term storage. So let me back up a little bit here. I want to make one more point here. There's the second row, which is a row major format LZ4. Which is about 4.7x compression. Maybe with sequence file it was like 4.5x compression or something. The only reason I mention it now again is what we also noticed was where when we are reading and writing sequence files, even though the compression factor was less, LZ4 was incredibly fast. It was faster than reading and writing uncompressed data. That's what we found for our specific data sets. So we ended up using LZ4 as an intermediate file format through all our job and through all our DAGs. So if you guys haven't tried LZ4, I think you guys should definitely give it a try. So we are back to system overview again, but this time with a little more data. So we have on the left, what you see is on each of these data centers, we have event stream flowing in. And there are these, there's a subsystem called XMP, which is consuming these events in real time and doing some lightweight indexing. And the output of that indexing is going into serving indices over there. XMP is also writing data over to DHR, which stands for Data Heavy Rainbow. Data Heavy Rainbow then writes this data over to Storm in real time, where this data is consumed by near real-time workloads for indexing and alerting. DHR also writes this data via HDFS proxies into Hadoop HDFS in the form of minute Avro files. Now on Hadoop, we divide the data store in two different parts. One part is ODS, which stands for Operational Data Store, and Warehouse. In the Operational Data Store, the retention is comparatively lower. We might just keep data for a couple of weeks there. But the latency of the feeds available is also low, so which is preferred by a lot of incremental indexing consumer needs. So there are a lot of people who are running jobs incrementally, and they prefer low latency environment. The data in ODS is mostly Avro formatted. Then the data eventually moves from ODS into warehouse for long-term storage. So on the move to warehouse, the data is processed, basically deduped, it's sorted, and it's recompacted into ORC file format. The blue boxes here show various workloads that run on our systems. One of the workload which is not highlighted here is the incremental indexing workload, which works off of ODS. There's also this re-indexing workloads which could be triggered either by having new algorithms or rules that might demand us to go back and reprocess the old data, but also by any bugs that might have been discovered in the earlier indexing approach. There are analytical workloads which basically run, and these are for metric reporting and monitoring the features. There are also some offline learning workloads for machine learning and data mining. See, all the workloads apart from the analytics workload, all the other workloads ultimately create some sort of offline indexes which are then used for improvement of user experience of Yahoo Mail users. So again, the system overview this time with more metrics. The event stream deposits about 2 billion events per day into XMP. The latency observed on XMP is less than 50 millisecond. The payload is mostly JSON format. DHR deposits about 7 to 8 billions onto Storm every day. The reason why the event count has dropped here is because for the streaming processing, we don't consume all kinds of events. So that's why you see that drop there. The latency here is 1 second. Bear in mind that this could be data from Singapore coming to like Buffalo within that 1 second. This is a batch of records. Then DHR also deposits this 20 billion events onto Hadoop HDFS. The latency that is observed on HDFS is about 2 to 3 milliseconds. I would say 3 is an upper bound. The amount of data that's deposited here is about 300 terabytes uncompressed per day. And the file format is Avro. Again, ODS daily, we add about 50 terabytes compressed Avro data to ODS daily. And then to the warehouse, we add about 40 terabytes of compressed data daily. This data is more tightly compacted. So, so at our scale, while we plan to run all the systems, so scaling is one of the biggest issue. We pay a lot of careful attention to design all the components that they would scale out at our scale. But after all the planning and efforts, sometimes things break. And next, I want to talk about an issue that we faced last year regarding some of our jobs. All right. So the issue here was there were some jobs which were creating excessive, which were making excessive requests to name node in a very short time span. So what essentially was happening was these jobs under question were a bunch of Hive queries, and these were either reading data from ORC files or Avro files. The data sets itself were between like 25 to 35 terabytes per day compressed. And the Hive queries were generating excessive file system open calls, which were essentially ending on name node, putting name node under extreme stress. The symptom here was that the response time from name node had degraded, and thus that degradation was affecting not just this job, but all the other jobs on the cluster. So in case, so like I mentioned, this issue was observed with both ORC files and Avro files. But in case of ORC file, what we observed was for our newer data sets were running fine, but one of our oldest data sets we were seeing this problem with. What was happening here was in that particular old data set, when writing that data set, we were using a default stripe size of 32 MB. And the reason why this was happening was because we had bundled in a very old Hive sort.xml in our job. The second issue that compounded the problem was ORC under low memory conditions was creating even smaller stripe sizes than 32 MB, and this was noticed while we were profiling the data files that were actually produced. And the third problem was that on the read side, the split strategy was set to hybrid, and at runtime it resulted into ETL strategy. What ETL strategy it essentially does, it creates one split, that's a mouthful, one stripe, one split per stripe. So the solution here was rather simple. We are already doing it for the newer feeds. We started using larger stripe sizes. We also started allocating more memory to the tasks that were writing out ORC files. The split strategy was set to BI, which essentially created one split per file, at least at that time. So, and that solved the problem for the ORC files. Now for Avro files, we had similar issue, but a little different. So with Avro files, what we do is when we create these data sets, we store the Avro schema files in HDFS schema URL, which is an HDFS, in Avro schema URL, which is an HDFS location. And we had anticipated that a lot of consumers will be accessing these schema files simultaneously. So we had increased the replication factor on the schema files to a very high number. Also, the Hive documentation seemed to suggest that. But the problem is when users are running a job which launch 30,000-40,000 mappers at a time, and they all try to open the schema file, even though the load is distributed across data nodes, but all of those mappers hit the name node within a very short span of time. And the name node has to return back with location of all these files. And with a highly replicated file, there could be a lot of location metadata associated with that file. So this can put additional pressure on the name node. This can also contribute towards saturation on the outbound network link on the name node. That's what we learned. So the option here was we could change the replication factor to some smaller value. But the main issue still was that there were too many mappers trying to open Avro schema files at the same time. So something had to be done about that particular issue. So the solution here was to store, first solution was to store the Avro schema in table properties in Avro schema using Avro schema literal property. The problem here was the meta store itself was backed by Oracle and storing these properties in the Oracle varchar schema, varchar column, and that had a limit of 4,000 characters, and our Avro schema wouldn't fit into that. The second option was to use strict Avro Serde, which was this was something that was developed at Yahoo, and it has since been deprecated even at Yahoo. But what it essentially did was when you create a table, at time of creation it would read the schema file, and it would materialize that schema into HCAT schema. But then going forward, all the changes that you need to make by using a Hive interface. Now, this was something that was not a very desired solution from application team point of view, because we already had many components in those systems that were relying on Avro schema file, and we did not want to have another source of a schema to be there. So what we did in the short term was we controlled the number of concurrent mappers. The map reduce job running, the map reduce .job.running.map.limit. We set that to 5,000. That somehow solved the problem in the short term. A few days later, our excellent Hive team at Yahoo, they came up with this new optimization. Hive optimize update table properties from Serde. What that essentially did was during the query planning phase, it read the schema once, and then it serialized it stored that schema along with the serialized logical plan, and sent it to all the mappers during the launch. So when we run things at our scale, we often need to. The point I want to make with this slide is when we run at our scale, we often need to make a lot of tweaks just so that our workloads can go through. I think the final takeaway I want to make is, like, when you're working with very, very large data sets, and when you are working with clusters that are really, really large, and workloads having access to really large capacities where one job can easily trigger 40,000-50,000 concurrent tasks, we really get to push the system to the limits. Occasionally, we do break things. We work with the Hadoop teams at Yahoo, fix things, and eventually contribute back to the Hadoop community. Now I'll hand over to Nick.
Thank you. So next, I'll quickly go over the second system I want to share with you. Remember, the first system that I just went through, the mail on grid 2.0, is meant for program consumption used by machine learning. The other system we built, Mail Analytics 2.0, is mainly used by people, professional Yahoo staff who are working on the product to try to improve. So the overall need that we felt was to do analytics at scale and at high resolution, so that we can understand our users and event, ideally one user and one event at a time. Also, but the other aspect of the scale is really when we have so much data and the complexity that comes with that much data, the data consumption actually, especially by people, can become a problem. Therefore, the system has to be self-serve. We need to much reduce the need for any intermediary in terms of the data delivery to the end user. And along the way, we also need to feed this data back to our system. For example, at the time a Yahoo Mail user logs in, we should have their profile ready so that the product can make some adjustment. So I'm going to go over, again, the design principle and thoughts that went into designing the system. First of all, we have the users in mind. As I just said, self-serve is a very important requirement. Also, the ease of querying. What that means is that the data needs to be easily understood so that they can query easily. Because of that, we actually came up with a new data model for the business in order to facilitate that. Also, we came up with, we tried to develop most of the features that are needed. Plus, we wanted to make the system that's flexible so that we can deliver features that we might not have thought of at the time of development. The other design principle that we adopted was efficiency, or the efficient use of our developers' resource. We're actually a very small team. Therefore, whenever possible, we feel free to use third-party tools, for example, BI tools that will produce the report queries so that we don't have a lot of custom query in our code base. And with that comes the need to have SQL JDBC compliance in the analytic engine that we use. The third thing is economic use of hardware resource. Again, with the scale in mind, any architectural decision we make or mistake we make might be amplified just because of the scale we operate. So very early on, we decided ETL, long-range reports or queries run on the grid, which is a proven scaling platform. On the other hand, to provide the best user experience possible, we also aggregate data. But we aggregate only at very high resolution, such that as far as the user is concerned, they feel like they're consuming data at very low granular, one user, one event at a time. And then we're very careful in assembling the system components based on what we need. For example, the way we chose our analytics engine is based on the most frequently queried patterns that we understand, which are there is the typical KPI slice and dice that every analytics system does. But there are also query patterns that are a little bit specific to our business. We have many use cases that need to do things with distinct accounts on very high cardinality. What I mean by very high cardinality, I'm talking about 300, 400, or more million in terms of cardinality. So we need to do discount join, distinct counts at that level. The other thing, similarly, we need to join on that very high cardinality to deliver the features that we in our system. And also, we're very because of the nature of our application, we need to have the clickstream analysis features that we need to develop in mind. So these are the query patterns that we care the most. And from that, we actually assemble a fixed set of benchmark, both 24 of queries and a few terabytes of data sets. And we use that to benchmark against the options at our hand. And this is the system architecture that for our analytics systems. The thing that's highlighted in red, where we say 90% of queries actually happen in the cache layer. That's a very key part of our system design. The other part that's interesting is that these two green boxes, they're the same. So we have aggregate layer both at the warehouse level and at the cache analytic engine level. The reason is very simple. We can easily replace that component and maintain the data integrity of our system. So largely, we deliver on our design goals. A third of our queries in production today, they have query turnarounds within 4 seconds. And that's the benchmark we use going forward. If we were to investigate other analytics systems, that will be the baseline. And also, we believe because of the performance of the system that provides a very good user experience in terms of interactivity, we have wide adoption of our system in a very short period of time. our system goes through as high as 2,600 queries every single day, used by hundreds of staff. With that, we're coming to an end to our session. And so the last one I will leave you with is that these are the various technologies that we use in our system today. And with that, that ends our talk. And welcome any question in the audience. Yes, please.
Hello. On the cache layer?
Let me repeat the question. In our aggregate layer, do we use SSD, and do we use compression?
On the aggregate layer, this is still on HDFS, so this is not SSDs. But on the cache layer, these are SSDs. And on both warehouse layer, as base layer, as well as aggregate layer, data is compressed.
And the performance is acceptable, as I just shared. Yes, please.
I have two questions. First question is, what do you use as an ETL tool on Hadoop? And the second question, what do you use for memory caching for queries?
OK. So the question, let me repeat. The ETL tool we use on Hadoop. The other is what's the component we use in our cache layer, right?
So as far as ETL tools goes, this could range from a variety of, like, traditionally we used a lot of pick scripts. We also use a lot of Hive. We do a lot of custom UDFs, a lot of MapReduce. But that's and Uzi for scheduling. That's roughly how our ETL stack looks like. In terms of caching, today we use Amazon Redshift. We continue to evaluate different analytical engines out there. We just store a small subset of data on what we call this as a caching layer. But we always are looking for better, more efficient, and cheaper solutions out there.
Yes, please.
So in your warehouse, in your data center, do you just copy the entire data of mailbox to the warehouse using the Hive framework?
So the various events that are generated on every time you interact with mail, you generate various events. All those events do create an event in data centers. All these events are then copied over DHR to the warehouse. Yeah.
So you mentioned that you're using Redshift as a caching tool. That must be running outside of your Hadoop environment.
That's true.
Do you migrate the data to Redshift?
Yes. So like we said, if we back up a little bit.
I don't have it here somehow.
Okay. So on Yahoo HDFS, on Yahoo Hadoop layer, we first run all our ETL processes, all our cleansing, all our processing, all our transformations are done on the Yahoo warehouse. And from there, we build aggregates. And after that point, after the base layer computation is done and aggregates are done, we apply no more transformations. So that allows us to quickly migrate that data directly to any analytics engine that we want to consider. The data is loaded directly from Yahoo Hadoop systems to S3. And then from S3, the data is copied over into Redshift.
Oh. Okay.
Thank you.
Thank you very much for attending. Thank you.